My talk will be about writing and analyzing network services of iOS applications. This work is done in collaboration with Shanghai University, University of Adelaide, University of Virginia, Nanyang Technological University, Macquarie University, and PWNZEN Information Technology. Network services used to provide network data storage or other online functionality to applications. Network service is widely used in mobile application. It's used for mobile device management, receive command from a peripheral equipment, file delivering, voice call, etc., or file or media sharing, etc. Here's an example that the Waze app projects its UI to e-vehicle device via USB connection. In the meantime, in order to receive touch events on the e-vehicle device, the app turns the device to a server. It's observed that the smartphone application that provide network service introduce significant security and privacy threats for users. Till now, lots of previous work have studied the security of network service of Android application. However, none of them focuses on iOS applications. So goals of this work are writing and analyzing network services of iOS applications and understanding network services of iOS ecosystem. There are three challenges with writing and analyzing network services of iOS applications. The first one is that the public repository of iOS application is not available. The second one is that the practical tool for automatically analyzing iOS applications are not well developed. And the last one is that the network service libraries of iOS applications are not available. According to these challenges, we designed an efficient and scalable iOS collection tool. Writing process that include dynamic analysis, static analysis, many confirmation steps, and a network service library identification method. The pipeline of iOS app collection include 4 steps. They are clouding, DRM protection, removing, executable parsing, and storing. We emphasize that we download apps from iTunes App Store by utilizing iTunes DLL file and decrypt the app by only delivering executables to speed up the collection. The proposed method enables large-scale apps collection with limited iOS devices. It can decrypt over 5,000 apps per day with only 2 jailbroken iOS devices. 160,000 iOS apps are collected in 1 month for later study. Our writing process starts with 1,300 popular apps. We firstly use dynamic analysis to select apps contain remotely accessible network service. Then use static analysis to check network service in these selected apps. And last, we verify the analysis result manually. We first dynamically check which app provides the network service by inspecting the network interface. By implementing an add-on for jailbroken iOS device, we direct the an API calls to writing code, and the writing code passes parameters of this API. The code stack is preserved by our add-on in the meantime for later network service library analysis. 3 categories of network interface are expected by dynamic analysis. For network service using dynamic port or loopback interface, the writing code considers the network service as safe and terminates the analysis. Network service using line interface is accessed remotely and will be selected for later analysis. Dynamic analysis reports 8.69% of the top popular apps use line interface on launch. Static analysis is performed on apps selected by dynamic analysis. To analyze iOS app, we optimize the open source framework by supplement semantics with more ARM instruction to the decompiler, convert interprocedure data flow analysis to on-demand interprocedure, and specify rules for checking the misuse of network service. The optimized static analysis framework takes 54 minutes for each app on average. This figure shows the static analysis result of checking the misuse of a GCD web server library. The green item in the figure indicates a harmless usage of this library. The brown item reports another misuse of this library. We emphasize that we adopt a writing process of dynamic first, static later, and manual confirmation last. The rationale behind the writing process is that dynamic analysis can rapidly check for misconfigured network interface on a large scale, allowing us to pinpoint a small portion of candidate apps. The more time-consuming static analysis can then be used to perform a fine-grained analysis and check for potential vulnerabilities. Finally, we verify the identified vulnerabilities manually. In order to analyze the ecosystem of network service iOS applications and perform large-scale analysis, we build signature for network services. First, we map the code stack preserved in static analysis stage to app code. Then we travel the pointer in the code stack from top to bottom until we find the API the app code evoked. As shown in the left box of this figure, we travel the code stack from item 0 to 27 and stop traveling at item 1, as this pointer points to app code. By checking the target API of the app code evoked, we get the system API, but in this case. To identify third-party network service library, we further map the code stack to token. The token is composed by strings in app code related to code stack. Since apps use the same third-party library have similar code stack, we compute the similarity of these tokens. Considering the app code, the pointers point to is always a mixture of developers' code and third-party libraries code. The token collected is also a mixture string from developers and third-party libraries code. To reduce noise induced by the developers' code in similarity analysis, we propose a weighted added distance algorithm to emphasize the third-party libraries string. The string related to the third-party library is assigned a larger weight and vice versa. To factor in the weight, we duplicated the string multiple times according to the weight assigned to it. After that, we measure the similarity ratio R of the code stacks by using different new tokens. Experiment reveals that the weighted added distance can increase the ratio R of the code stacks for the same network service library in different apps, but has slightly less influence for different libraries. Empirically, we identify third-party network library if the ratio R is above or equal to 0.6. After we recognize the third-party network service library, we select the prominent string by leveraging the TF-IDF algorithm. The selected string is used as signature for identifying third-party network service libraries in apps. By taking signature or system network service library, we analyze the network service for iOS ecosystem. The table depicts that the network services are prevalent in iOS apps. Over 40% of apps potentially evoke system API to provide network services. The results show that the apps in China are more inclined to provide network services than those in the United States. We found that apps in game categories are inclined to provide network services. By taking signature or third-party network service library, we found the distribution of third-party network service libraries in iOS applications. For example, we found game category mainly use Qualcomm HTTP server, Tipjoy Qualcomm HTTP server extensions third-party libraries to provide network services. We further studied the association of network service libraries and get the layout of these libraries. Vulnerabilities we found among the 1,300 popular apps fall into 4 categories. They are connected with the IoT device with no or weak access control, served as a command server to execute command per the client's request, served as a file server to share files between a desktop computer and an iOS device, and served as a node of CDN networks. We further identify vulnerabilities related to third-party libraries and summarize them into 3 categories. They are use vulnerable libraries, abuse, out-of-date vulnerabilities, and misuse of libraries. We prepare a video to demonstrate the vulnerability we found in this app. In this video, we send touch event remotely to manipulate the app. The message can reset destination to alternative places. The network service is pervasive that an attacker can even probe and attack iOS devices with running in cellular network. Okay. Our conclusion is that network services is widely used in iOS applications and vulnerability are widely exist in these network services. In this work, we found 11 vulnerabilities in 1,300 popular apps and 92 vulnerabilities in the whole dataset, and 2 CVEs are assigned for our finding. At last, we propose mitigation strategies for developer, network operator, and system vendor, and hope that our findings can motivate stakeholders to focus more on the security of network services of iOS applications. Okay, thank you.